Welcome to Did You Know? The ESCO HVAC Show. We will see you in about 45 seconds or so. Make sure that you are subscribing to our channels, our LinkedIn, YouTube, Facebook. Turn on notifications, and we are very excited to be here with you. It's almost time, about 30 more seconds. Make sure to grab your notebook and pen so you can jot down notes along the way, because at the end of the show, you could have an opportunity to ask our guests questions so we can dive a little deeper into these topics. And here we go. Welcome to Did You Know? The ESCO HVAC Show. All right. Thank you all for joining Did You Know? The ESCO HVAC Show. Jason, how you doing today?
I'm good. Thanks for having me on today, Clifton. I'm sure we have some awesome stuff planned for today. I'm very eager to jump in and see what we got.
You're the man to help join this conversation, because this is something that I'm pretty passionate about, but I know you are like super passionate about. It actually comes from a question, a concern that came from one of our viewers. Rick Kinsel out of Coburn Supply calls up and says, "Hey, I love that flammable refrigerant video. Now I've got my contractors that are asking, what about the glide and the fractionation of 454B and 32 when it comes out?" And I said, "Woo, man, now there's a topic that we need to dive into, because a lot of people don't even understand fractionization, and they don't know what glide really is, because we didn't really worry about it with 22, and we didn't necessarily even think about it much with 410, even though it was there.
It was so small.
It was so small. We'll actually go over that, how close that little window, that glide is. But we're going to see more blended refrigerants in our industry, right, as we move forward. A lot of HFC blends, HFO blends. We're going to see some glides. And then those of you that are in refrigeration, you already know that there's a lot of refrigerants out there that have glide to them. So we wanted to help clarify that a little bit. We wanted to dive into it. I even put us together a new video that I think is even better than the flammable refrigerant video. That's going to be at the end. It's basically going to be kind of a recap, but from a different perspective of what we're talking about here today. So today's conversation is going to be about refrigerant, glide, and a lot about that whole potential for fractionization inside of a refrigeration system. So I guess, Jason, let's just start like from ground zero. And let's just talk about refrigerant inside of a refrigeration cycle. And all of these slides should be familiar to those that teach the EPA 608. This is the updated EPA slides, which will be out in the near future. Maybe have some things cooking here. So these pictures will be familiar, though. So this entire content is basically like a deep dive and recap of what we talk about in our 608 classes. So in our refrigeration cycle, we know that half of our system tends to be in liquid, and half of our system tends to be in vapor, or a combination of liquid and vapor, right? In between our compressor and our metering device, we split our system.
Saturated, right? Yeah.
Saturated. So when we're in liquid stage, even if we have a blended refrigerant, there's just different chemicals, different refrigerants that are all blended together. In the liquid stage, it's all one component. You know, we've all came to that saturation point. We are in a liquid stage. When we are boiling off, once we have met that saturation point, say we're a liquid and we're going to vapor. When we meet that saturation point, that's when we start boiling, right? And if we have blends of refrigerants, maybe the refrigerants get along and form a new boiling point, a new saturation point, or maybe they have different saturation points, because they're different chemicals, right? That's when we get into the Z-tropic and the azeotropic, and we'll talk about that. So when we're talking about this refrigeration cycle, and we're talking about refrigerants, and our new refrigerants in particular, we are going to be replacing R410A in new systems. And right now, Jason, do we have anything to replace 410 for service gas?
In existing equipment? No.
Yeah, no.
The only thing that should go into a 410A system right now is 410A.
Yeah. So it's going to be a crazy world when we start talking about this new equipment and new refrigerants like R32 and 454B. which really the R32 is not too unknown to us. Like 410A was
Right.
half of it was 32, the other half was 125. So it was a blended refrigerant. So R32, we really not going to have to worry about our fractionization or our glide a whole lot because it's just not there. But with 454, we're actually going to take R32 and we're going to blend it with 1234YF. Right?
Well, we're not, but the chemist is.
Yeah, absolutely. Because there's different, very specific proportions, and the science behind blending refrigerants is a big deal. So all of our 400 series refrigerants and 500 series refrigerants are blends of different chemicals, different refrigerants. So what happens when we start looking at the refrigerants as they're going through phase changes, right? So if we think about like when we're in the condenser, whether it's the outdoor unit in AC or whether it's the indoor unit in heat pump, heating mode, when we think about what's happening in the condenser, we are coming into that condenser with vapor, right? We're going to desuperheat it. We're going to change its state back to liquid. And then we're going to cool it down a little bit more just to make sure it's all liquid, right? We don't want that mixed gas going over to a metering device. Vapor doesn't do anything through a metering device for work. It has to change state to do work. So we need all liquid, right? Now at that condenser. Well, if we have a blended refrigerant, and if it has different boiling points within it, that means in that condenser, we have that potential for one refrigerant to start condensing before the other refrigerant. Right?
So far, so good. I'm with you.
Okay. So what happens if that's a big window, right?
So you said something. You said 2 boiling points.
Yeah.
By definition, what is that?
It's our saturation. That's when we change state because we boil or we condense at the same number, the same point.
So if we have 2 different boiling points, the difference between those 2 boiling points is our glide.
Aha. Is it that simple?
That's what it is.
Okay. Right, it is. And that's why I love teaching this because it's so much easier than we allow it to be. All we're really talking about is it's a window in between those 2 points.
In the image you're showing here, whether it be the evaporator or the condenser, that's where our glide and our fractionation tend to really jump in and say, here I am, is when we're changing phase, either from liquid to vapor or vapor to liquid. Like you've shown here in the condenser, we're going from a vapor to a liquid. Yep. And then the evaporator or the cooling coil, if you will, in a heat pump, we're going to go from a liquid to a vapor. And this is where glide rears its ugly head, so to speak.
Aha. Now we're getting somewhere, right? Because it's not really in the entire system. It's very much in that phase change that we start seeing these opportunities for glide and fractionation or fractionization that you may sometimes hear. They both really stand for the same thing, the separating of chemicals during phase changes. So let's talk about that for a second. If we step back in time, when we transitioned from our single constituent refrigerants like R22, HCFC 22, over to our HFC 410A, there was a big scare about this glide and about the potential of fractionation because 410A has 2 different chemicals in it, R32 and R125. And so depending on where you are on the pressure spectrum, remember the lower the pressure, the smaller our glide potential would be. The greater the pressure, the greater our glide potential would be. There was actually so much of a scare over fractionization of R410A that I won't say any names, but I will say that I was working with a manufacturer that at that time when we first went to R410A equipment, if you had a warranty evaporator and the leak was in the slab itself, they had a calculation table that went along with it. And with that new coil, you got a new filter dryer and you got up to 5 pounds of R410A as part of the warranty procedure because there's the scare of fractionization. So what is that? What is fractionization? Well, let's get a little bit closer to this topic, okay? So let's talk about a PT chart. Jason, I'm sure you grew up with a standard fold down PT chart, didn't you?
Yeah, in my pocket.
That's right. A lot of times we use our PT chart where we're in the field. We kept it in our pocket. We unfold it to see where we were at. Now we use digital gauges. We use apps. We have a lot better resources. But
Digital, right? Yeah.
a lot of digital resources available to us. A lot of our manufacturers have phenomenal apps that will show us what these are. But what we're really doing with that PT chart is we're simply looking at the pressure and the temperature relationship because they are very consistent, right? Well, with a single constituent refrigerant like R22, since there is no glide, there's only one number that it corresponds to.
One pressure, one temperature, a boiling point or a condensing point, saturation temperature, if you will.
It's exactly right. So if we looked at this particular chart and say it was a 70 degree, so that was the saturation set point, and our R22 was at 121 psi, vice versa. If we put our gauges on, we had 121 psi. Well, that was a 70 degree, right? It goes both ways. So here's the thing. When we went to R410A, we added a window in there because now it wasn't an exactly single number. It had some variation to that on our PT chart. But it wasn't far enough that we talked about it a lot. Right?
It didn't make sense to print side-by-side charts of liquid and vapor when there was such a small deviance from one. I mean, the plus or minus accuracy of your instrumentation was bigger than the glide on 410A.
Yeah, just did a really good podcast with Eric Kaiser from True Tech Tools. It'll actually be released this Friday. So coincidentally, you want to check that out and talk about the accuracy of tools from 5 years ago, 10 years ago, 20 years ago. Great podcast to listen to. So definitely hop on over. That's Did You Know the ESCO HVAC podcast, available on every podcast network. Plus it's on our YouTube channel as well. So check that out. So what we're talking about is those earlier PT charts for R410A, there wasn't a window there. You just had a number, like it was a single constituent refrigerant. But it really wasn't. It actually did have a glide to it. Just enough that a particular manufacturer for sure was afraid that if we had a leak, let's go back to that evaporator slide just for a second. If we had a leak in the middle of that evaporator, in between that phase change of those two refrigerants, if it was in the exact right spot and it was a slow enough leak, we could potentially leak out one of those chemicals before the other one.
The higher pressure one, right?
Exactly. So it would change the chemical composition of our refrigerant. So it would no longer be a 50-50 blend of 32 and 125, it would be bonkers. Who knows where, right? So it wouldn't be accurate to be able to measure and may not even function properly, may not have proper oil return.
You would probably have some capacity loss as well.
Exactly. So
I do want to point this out while you're on the composition and things. So the two refrigerants that we talked about that made up 410A, 32, 125, there was a common misconception out there that the fractionation was so bad that if you did have, like you mentioned, the hole in the line in the right spot, and we lost enough of it, that all of a sudden all of the R25 was going to leak out, and only the R32 was going to be left, and it would go from an A1 refrigerant to an A2L.
Well,
that's wrong. Right.
Yeah.
When ASHRAE does their testing, they fractionate as best they can any blend, every blend. So they beat it up, leak it out.
Forcibly try
right.
to.
They are really trying to get this refrigerant to fractionate, and then they do the flammability testing. It's called the worst case fractionation potential. Yes. So if a blend has an A1 rating, it's going to retain that A1 rating even if there's a leak.
Exactly.
When they test it, they beat it up pretty bad and then test it. So I just wanted to dispel any myths about that one.
I'm glad you did, because we really need to bring that up. I was concerned myself when I started talking about this 454B, because we're going to show you here in a second the differences between 410A, 32, and 454B. And there is a much wider window, a much wider glide with 454B than we have in 410. And so I actually reached out right to the manufacturers, and talked to Dr. Chuck. Dr. Chuck, what are we going to see here? And he says, well, did you know that ASHRAE does this very extensive worst case scenario testing, exactly like Jason said? And I said, I did not know that. I assume they did, but I didn't know what that accounted for. He said, yeah, there are refrigerants that have very wide glides, and we'll talk about that in the video later, that could have some potential to change the composition and potentially change the flammability rating. He said, but when we're just a few degrees, it's almost never going to hit that scenario.
Correct. Yeah. So if it gets an A1 rating, it's going to stay an A1 rating.
Exactly right. So it brings up the question, do we replace all of the refrigerant if we have a leak in an evaporator and we're concerned about fractionation? Well, I personally always say, if I am opening up a system, my best practice is to replace the filter dryer, proper evacuation, and new refrigerant, if at all possible.
If you're recovering from a system that has a leak, you're probably pulling in air through the leak. So anything that's in that recovery tank is going to have air in it, correct? So as you said, best practices would be to recover from the system, find and repair the leak, evacuate the system, and then recharge it with fresh refrigerant.
Exactly. So our manufacturer has clarified, not in writing, but in verbal, that no, there is not that potential for changing the flammability, and we're not going to degrade the composition. So it is not required to replace the refrigerant, but it is always a best practice in a leak scenario. So it helps clarify that a little bit. So let's look at what that fractionization is. And by the way, everyone that's hopping in, let us know where you're chiming in from. We always like to see how big this community of HVAC and refrigeration, professionals are. I'm chiming in from Brownsburg, Indiana. Jason, where are you at?
I'm in Crown Point, Indiana.
I see Howard out there. He's chiming in from Denver. We've got Illinois. So yeah, let us know where you're chiming in from, and we'll try to throw it up down here at the bottom of the screen.
Just to point this out, this entire show today came about from somebody chiming in and asking a question.
Exactly. We want to know your feedback. Like, this is our mission, to help understand things that are not exactly clarified. I mean, here we're talking about slides from the EPA that we did years ago that is just as relevant right now as ever, right? So anytime you see something that needs clarified, let us know. And we have fun we get paid to do this stuff. Are you kidding? This is like the best job in the world. And speaking of fun, you have to stay around for this video, right? So this is like the special preview, right? As members of our community, you get to view it before anybody else does. So make sure it's going to be a lot of fun. I had a fun time doing this one. And it's all relative. It's all back to this point. So let's talk about our two different types of blended refrigerants, right? This is all very relevant when we're studying our EPA 608. We really have two different types of blended refrigerants, and it all comes down to how well do they blend, right?
Do they play nice or not?
That's all that it comes down to. If I take two different chemicals and blend them together in a lab under, I don't even know exactly what the perfect circumstances are that's used in a lab environment to be able to make this magic happen. But when we do, some chemicals will completely, even if they have different boiling points, different saturation temperatures. I say boiling. I shouldn't say that. I should say boiling and condensing. Saturation. Right? That's what saturation is. Above here, I'm boiling. Above there, I'm condensing. But it's at a point. So if I have those two chemicals and I blend them in a lab, and the new chemical has a fresh new boiling point, that's where I'm going to call that an azeotropic refrigerant.
So think of it in mathematical terms. It's A plus B gives you C. We put these two together and we get this whole new product.
Something new. It might be in the middle. It might be offset. It just depends on the chemical properties. But it is one number, right? It is two that become one and act like one.
They behave like one, correct.
That's right, right. So that is all that it comes down to when we're talking about azeotropic chemicals and refrigerants.
And those are our 500s.
Every 500. If you see a 5 in front of it, it is a blended refrigerant that when it got together, it said, I like this. Cool.
And they stick together. No glide, no fractionation, act like R22 or
R134. Like a single constituent refrigerant.
Right.
On gauges, you don't know the difference, right? That's really cool. Doesn't happen all the time, though, right? Most of the time, it's like a family get together, right? We all get together, we get blended up, and we deal with each other. And we all have our own points of view that we may not want to budge from.
Right.
Right.
So again, in mathematical terms, like we said, the azeotropes were A plus B gives you C.
Yeah.
And this one would be A plus B gives you AB. The
That's
resulting mixture retains properties from
of the
the original.
Exactly. Right? So if they're very close, that's cool. Like 410A. If it's really close, doesn't make much of a difference.
They call that a NARM. A near azeotropic refrigerant mixture. Still a 400.
Yeah.
Still have some fractionation potential. Still have some glide.
Yep.
Not quite an azeotrope, but real close to it.
Super close.
But still a azeotrope nonetheless.
Well within 1 degree at any common refrigeration pressure set point. So R410A falls into that class, right? So we didn't worry about it too much. Hopefully we knew about it. And if you didn't, now you do. But now we need to know what that looks like when we have bigger glides, when our family doesn't get along quite as well.
So just to point out, the glide on 410A is right around 0.3 degrees.
Yeah.
So, I mean, again, in the plus or minus of your instrumentation, your gauges, your temperature sensing devices was within a half a degree. The glide on 410A is a third of a degree.
Not even
3/10, yeah.
Yeah. So we treated it like it was a azeotropic refrigerant, right? So that's the reason we give it that near azeotropic. All right. And that could be 2 different chemicals. So if we take R410A would be considered a binary, two different chemicals near azeotropic refrigerant. I could have 3 parts, and I would call it a ternary blend, and it keeps going on, depending on how many chemicals.
Yeah, we've seen some today that have 6 or 7 or 8 different refrigerants in there. I don't even know what you'd call those.
I worked at a place that made one that had a whole bunch of them like that. And so then when you look at the glide, you go like, I have to know what I'm calculating when I have a bigger glide. That's all. Right? So how do we do that? Yeah, let's talk about that. Okay. So that glide is representing the difference, the window between our different boiling points. So let's just say I'm going up, all right? Let's say I'm in the evaporator and I'm going from a liquid to a vapor. Well, I should say going down. I mean, our pressure is going down, but if we look at our concentration of our refrigerant, as we start evaporating, say I have one of my chemicals does its evaporating right here, right? This is its saturation. And my other one takes a few more degrees before it gets there. And it saturates right here. That means all of this space in between these two is glide, right? So if I looked at this one down here, and so let's just assume this was 30 degrees. I'm just giving it a number. And this one up here was 32. That meant that this chemical started boiling at 30, and it was all vapor. And this chemical didn't start until 32, and it was all vapor from there up. That means from here up, it's all vapor of both chemicals.
So you start your superheat there.
Right here, right on the top. And we're going to give it a name. We're going to call it the dew point. Right? That's the top. Right? Because what happens to moisture at that point, right? That's like dew, like morning dew. Above it, above that point, it's vapor. Below that point, it's working its way down to liquid. So that is going to be your dew point. That's the top. So here's that same window. So let's think about this one up here. If it was going the other way and I was coming down and I hit 32 degrees, at 32 degrees, I would now condense to liquid. And from here down to here, I would be liquid. But this one didn't start until 30. This one was still vapor in that whole window. So once it got down to 30 degrees, it condensed down to liquid. So that would mean this point here down is all liquid. So the bottom one is where we would start calculating for our subcooling, because that's really the only point that we started becoming fully liquid.
Right. The entire mixture is now liquid.
That's all it comes down to.
In that window, we're still saturated.
Yeah. we're working in there, right?
Right. Something might either be condensing or evaporating. Some might be already fully evaporated, depending on how many chemicals are in the
Yeah.
blend and the difference in all the boiling points. It could be complex.
What if I've got 4 or 5 or 6 different chemicals all blended together and every one of them has a different one? We got 30, we got 30 and a half, 31, 32, 32 and a quarter, 33, 34. It could be all over the place. So we can't calculate anything in the middle.
Until the phase change is complete.
Right. In design, we can see another component of that. Called midpoint. Jason, would you like to run with that one?
So what a lot of manufacturers have been going towards is something called the midpoint.
Mm-hmm.
And it's usually different for the condenser versus the evaporator, or where you're condensing refrigerant versus boiling the refrigerant if you're in a heat pump.
Right.
And for the condenser, it's usually a 50-50 split. So
put it in the middle.
Right. Add up the dew and the bubble and divide by 2, and that's your 50% average. All right. On the evaporator side, because of the metering device and flash gas and things of that nature, it's a weighted
different
average. Right.
Yeah.
We're going to do 60% of the dew point and 40% of the bubble point, and then add those two together. Okay. A lot of the manufacturer software, when you're sizing equipment, when you're trying to build a walk-in cooler or something, right, they will actually, if you're using a blended refrigerant, will typically go with a midpoint. And not all manufacturers use a weighted midpoint for the evaporator.
Yep.
Some do. It all depends on the metering device and the blend and the how big is the glide. But a lot of manufacturers do use weighted midpoint on the evaporator side and a 50-50 or an average, if you will, on the condensing side.
Makes sense. I mean, it's just kind of in the calculations of it, right? We know that it's happening in there. So we're just going to make sure, and most of those designs have got a fairly wide superheater subcooling to help compensate for that as well. But it at least gets us a midpoint. It gets us a design start point.
And some of the gauge some of the software that we're seeing out there, when you hook your gauges into a system, your digital probes, and you're feeding to an app, some of the apps that are out there for working in these systems will actually display the midpoint temperature instead of the dew or the bubble. They'll actually display the midpoint instead.
And that's why we want to talk about this, is because many of our digital gauges are going to calculate all this for you. You're not going to have to do it. But if you are in if you're in a lab, if you're in school, you're wanting to know exactly what's going on, this is what we're doing. You
do need to know the difference between dew, bubble, and mid. I mean,
absolutely. It's very different places.
Different apps are going to show you different numbers and different temperatures or different pressures. This is the midpoint temperature. This is the bubble point temperature. This is the dew point temperature. So you have to understand what those are.
Yep, absolutely. So there's a little bit different representation of what we're doing. So below the bubble point, you're going to be all liquid. Above the dew point, you're going to be all vapor. What's happening in between in the middle? A lot.
There's a series of evaporations. We have a mixture. It's saturated for sure, but some refrigerants are done boiling. Others have just started. It's a parade in there. Yeah,
exactly. So let's talk about what that's going to look like, particularly for R54B. Remember, R32, single constituent refrigerant, PT chart is just going to say, boom, here's your number, right? If you go above here, you're going to be vapor, and we're going to use that for superheat. If you're going to be below here, it's going to be liquid. It's going to be for subcooling. But our blends are going to see a little bit of range. So let's look at this one. So I was having a hard time finding some true PT charts. So I had to do a little backwards conversion to build this, but it's all there. So let's just assume, we're just going to play with numbers for a minute. Let's just assume we put our gauges on a system and had R454B in it, and maybe we had 100 PSIG, actual gauge pressure. What that would be telling us is that at 100 PSIG, I don't have a single number to calculate superheat or subcooling. I now have my glide between my bubble point and my dew point. And so anything below my bubble is going to be good for calculating subcooling, and anything above my dew will be good for calculating my superheat, right? I can't use one or the other if I don't know what they are, because now I can
have two charts now, is what you're saying. We have
big,
one pressure there on the left, and we have one for the liquid side and one for the vapor side at the same pressure.
Exactly. So I went a little bit further And let's do.
So if I could point out, if you look at
Yeah.
that pressure chart you got up there at 100 psi on the liquid side, 34.3, and on the vapor side, 36.6. So the difference between those two is about 2.3 degrees.
Yeah.
What
that's
is
not
that?
2/10.
That's the glide.
That's how much is actually there, right?
So it has a 2.3 degree glide.
Yep. Now, let's look at all three compared to each other, right? Oh, before I get there, remember 400 series, all the 400s that you know, 410, 404, 409, 407,
454B,
454B, 458. There's a ton of them out there. All truly have a bubble and a dew point. Even if it's near azeotropic, it's actually there. May not be on your chart, right? So we talked a little bit about what can potentially happen in that fractionization or fractionation stage. That means if one of our chemicals has started boiling and we had a leak on the top of a tubing, and so we had liquid in the bottom and vapor at the top, we could potentially lose one of those chemicals, right? It gets a little tricky with our new refrigerants, and we need to be very, very careful to understand that none of these refrigerants are interchangeable. Right?
Blends are created in the lab by chemists, not in the field by technicians.
And if I have even if the PT chart looks similar, right? Even if my R410A and my R32 and my R454B look similar pressure-wise, I cannot swap them. I cannot mix them. I cannot create my own new creation, right? By
There'd
law.
be no way to calculate superheat subcooling accurately. You may lose capacity. You may alter the compression ratio.
The flammability.
Right. So you're going from an A1 to an A2L.
Changes everything, puts you in a liability scenario.
There's a lot of things that happen internally in that system if you decide to just, let me mix this in here with that. And again, you don't know what the resulting mixture is going to make, what the temperature pressure chart's going to be, what the saturation. You'll be maybe close, maybe far off. There's no way to really know, right?
Right.
We may lose capacity. We may gain capacity. We might start freezing something or overheating something. I mean, there's no testing that's been done on this new mixture that you just made.
Exactly.
So you don't really know how it's going to respond.
No. But what we do need to know is how they look similar. Remember, this is all governed by the EPA too, right? And does not approve these refrigerants as substitutes for like 422 and 410A. These are only going to be used in new pieces of equipment. But they do have similar pressures. So we want you to see, we don't want you to be afraid. That's really what it comes down to. When we went from R22 to R410A, oh my gosh, these pressures are so huge, they're going to blow up.
And then the oil change, we went from mineral oil to POE oil.
Yeah, and is it medium temp? Is it high temp? We're not really going to do that, right? We're going to have two new refrigerants in new systems. We're not going to have an R410A system that has 32. We're going to have a new 32 system, or we're going to have a new 454B system. We're going to have some new 410A systems out there for a while, but we're going to see less and less and less and less of those, right? So let's look at it. Let's look at the differences here. If we took, let's go back to that 100 PSIG, just a scenario here, right? If I had R410A, here's your difference right here. I actually, even if my chart said 31.4, it actually meant that I had a bubble of 31.3 and I had a dew of 31.5. So even if your pressure chart did not show this, this is what it actually
0.2 degrees, right?
Yeah, this is what it should have shown, but because it was so close, we just said, forget about it. Just call it 31.4, right? So R32, a single constituent refrigerant. At the exact same pressure, it has a temperature of 30.4. It's only a degree off, right? It's not super drastic. If it was the new 454B, which is the blend of 32 and 1234YF, we now have a bubble of 34.3, but we have a dew of 36.6. So we have a 2.3 degree difference. So now we have to start factoring that in when we're looking at subcooling or superheat, because our new units are so much more critically charged than they have in the past. Sometimes down to the ounces, right?
That's what I was going to point out too. The other thing that can affect the system, again, if you're mixing refrigerants, is how much of the charge is being circulated. It all comes down to using the proper refrigerant for the right system, because again, the charge, as you mentioned, is critical in a lot of these systems. It really, really dictates the capacity and the efficiency of the system.
Yep, absolutely. So this is all we're going to do, is just understand that if we're doing subcooling, we just need to be below the bubble. If we're doing superheat, we need to be above the dew. That's all we're actually talking about. So
pointing that out, Clifton, moving forward, when we do make the transition to these new refrigerants at 32 and 454, these are pressures we're used to seeing daily anyway.
Yeah.
There's nothing.
We're not really changing.
Right.
We're actually going down a little bit.
A little bit, right. So again, it's something you've been doing already every day anyway.
Yep. Don't freak out of it. Come to the ESCO Did You Know show and learn about what's actually happening in front of you, so you're not afraid of it. Same oil. Yeah. I mean, what are we changing? If it happens to be an A2L rated piece of equipment, it's just going to have extra protections to make sure that there's no potential for ignition. We showed that last week.
I was going to say there was a video that was done.
Yeah, there's a video out there.
Brian Clifton there.
I'll put a link to that when we're all done.
Yeah. Watch that video. It explains it all.
Yeah, it's not super flammable. We're just adding some extra precautions. Don't let those precautions scare you. So 410A is going away, has a very high global warming potential, 2090. Right? We're going to be going down to refrigerants like R32 with a GWP of 675. We're going to be going to 454 that has a GWP of 467. Right? Some places you might not even see 32. If you have an area that requires a 500 GWP, which we've heard rumors of that in different places on certain pieces of equipment, well, then the only thing that's going to fit is a 454B. Right? 410A doesn't even have a chance, which is why we're going to see 410A go away. Its GWP is going to make it go away faster, I think, than anticipated. Yeah. All right. So what's the moral of the story? There is currently no drop-in replacement for our 410A.
The only thing that should go into a 410A system is 410A.
410A. That's it. A new R32 system is only going to get R32.
R32.
A new 454 is only going to get 454. So I can already hear, waiting for the hate mail. Anybody, I haven't seen a message yet, but I'm sure it's going to be, oh, we got to carry more jugs of refrigerant. I had 13 of them on the van when I was a refrigeration technician. Don't cry. Make room.
It's starting to be commonplace that we're going to see single application refrigerant use per. So this one blend of refrigerant works in this application. This refrigerant works in this application. We're going to start seeing very application-specific refrigerant blends, where we used to have R22 that could go in coolers. We would see them in air conditioners, heat pumps, walk-in coolers, reach-in coolers. We're not going to see a lot of that moving forward. We're going to see one refrigerant in this application, one in this application, that sort of thing. Very specific. So.
The air conditioning, residential, light commercial particularly, and even some of our industrial is going to look more like the refrigeration industry. That's all. You just have to know what refrigerant you're working with.
You may have still some R22 systems out there, and there are 17 EPA approved substitutes for R22. So I don't even want to get into that.
No.
And then we have 410A systems, and we're going to start seeing 454B and R32 systems as well.
That's all.
You have to read the data plate and see what's in it. I
keep telling people, if you don't believe me, just go to your local Costco, walk through the air conditioner aisle. Every single one of them's already 32, right? Our 454B, it's been announced, is going to be out here by the first of the year. So we're going to see it just in months. So just be prepared for it. That's all. All right. Those of you that hung in, are you all ready? Okay. Man, I had a lot of fun with this. I honestly, this was a good project, and it's a little, it's fun mixed with a little education, and I hope to do more of them as long as it meets everyone's expectations and requirements. And anyhow, all right. Ready?
Yeah, let's see it.
All right, here we go.
Well, hello everyone. Welcome to Did You Know, the ESCO HVAC show. There is a lot of talk about refrigerants right now, and we're here to help you understand all of these differences in refrigerants and how they impact you when we're actually out in the field using gauges to take temperature and pressure readings and set superheat and subcooling charges. And we really need to understand the chemistry behind these refrigerants. Did you know that all 400 and 500 series refrigerants are blends of other chemicals or refrigerants? I know, maybe we haven't been told that before. Even refrigerants like our R410A, R404, 409, 407, 500, 502, they're different blends of refrigerants. Sometimes they like each other, sometimes they don't. So that's what we're going to do. We're going to do some experimenting right here in the ESCO lab to help you understand what blended refrigerants look like, to understand what is Glide and what is fractionation. Are you ready? Oh yeah! Okay, so let's talk a little bit about Glide. Not everyone understands what Glide is. It's actually pretty simple. If we take two different chemicals that have different boiling points and we mix them together, either they are going to really like each other and they're going to have a new boiling point that is very consistent with whatever pressure it's at, or the two different chemicals are going to boil off separately. And that's what we find in the 400 series refrigerants. The 500, they like each other. I can take two different chemicals with two different boiling points, mix them together, and they are happy as can be. And so when we look at our PT chart, there's only one number that we reference because those two different boiling points have now came together and has a new common boiling point. But our 400 series refrigerants, it's not really like that, right? So let's do a little experiment. Let's take two different chemicals with very different boiling points. We're going to start with plain old water, and let's give it some color so we can actually see that it's going to be separate from the other one we're going to put in. Right? Okay, so let's give our water just a little bit of color. We're just going to pick on blue. Oh, that's some ugly looking dye. Ooh, isn't that cool? Right? Let's mix her up a little bit too, so that we get it all one consistent color. Now, we've added dye, which has a very high boiling point, so it's not really going to affect our different chemistry. We're just using the dye to show that we have two separate chemicals. Well, what happens if we take water that has a boiling point, and then we take another chemical that has a very different boiling point? This time we're going to pick on ethanol, alcohol, right? This particular one of choice is just clear tequila, right? So we're going to mix in some clear tequila, and if they like each other, they're going to be an azeotropic chemical, which means their two boiling points, even though they were separate, now have a new common boiling point, and they like each other. Well, what happens if they don't like each other and they just kind of live with each other? They deal with their differences. Well, that's where we have our zeotropic or non-azeotropic. That means they're going to be together, but not necessarily happy about it. And so they're going to boil off at different points. Okay, so we got our blend. We now have a new chemical. Well, that's kind of fun. I'm going to just leave that spinning just for the heck of it, right? Isn't that cool? Now we're going to add some heat to it, and we're going to see if we can separate these two different chemicals which have separate boiling points. One boiling point for water at atmospheric pressure and one boiling point for our ethanol at atmospheric pressure. So we're going to apply some heat to it, and we're going to give it just a little bit, and we're going to see if we separate the two of them. So that distance in between where one chemical starts boiling and then the temperature that the other chemical starts boiling, that window is called our glide. And it's the same way when we're coming back down, when we're condensing from vapor to liquid. One is going to condense before the other, and it creates a window in our glide. It's in that window that we worry about fractionation. Fractionation is simply the ability for our chemicals to separate while they're in that window. Meaning that if we had a leak and it was in the right spot, the right location in that point of our system, then we could actually lose one chemical in vapor form and the other would not be boiling yet. So if we were traveling on a pipe and we had liquid in the bottom and vapor at the top, but only one of our chemicals had started boiling, that means all the vapor on top is from our one chemical. And so there's the potential for fractionation. So we just have to be aware that all of our 400 series refrigerants and 500 series refrigerants have that potential. That's why we charge them with the can upside down, so that we are only putting liquid into the system just in case they happen to be different inside of our tank. So learning that glide and fractionation happens in that window in between the two boiling points is very important when we're setting superheat and subcooling of our chemicals. All right, let's see if we can get this bad boy to fractionate. So what we're seeing now is, as our chemicals are sitting here mixing, we don't have to mix them, but it looks pretty cool. We're applying heat so that we can raise the boiling point of our two different chemicals. And the goal is to be able to heat our ethanol up to the point that it boils, evaporates before our water does. If that happens, our ethanol is going to boil off into vapor form, and it's going to hopefully condense back down into our other container here so that we're actually separating the two chemicals. It's going to take a little bit of time as we raise this temperature, but we should start seeing that, and we should see the ethanol boil off before the water. It's pretty cool. Oh yeah, we're cooking now. So we are boiling off our chemicals. And as you can see, one of our chemicals is already condensing back down into a liquid over here. Now, which liquid is it? Is it ethanol or is it H2O, our water? So we're going to let this run for a little while and we're going to find out. And we're going to see if we have boiled off our ethanol and left our water, which means we approached the boiling point of our ethanol before the boiling point of our water, and we removed ethanol out in vapor form without removing the water. That's pretty cool. Okay, now that we're starting to boil off, let's monitor the temperature of our boiling and see what we have. See if we're actually boiling at 212 or if we're boiling less than that, like at the boiling point of ethanol. So we'll just add a simple K-type thermocouple. We'll put it on our boiling line. See if we can monitor this bad boy. I'm smelling a very familiar aroma. Smells like tequila. Okay, isn't this exciting? We're actually seeing it in action. Well, what are we actually seeing? Well, we're seeing that our ethanol actually has a boiling point of around 173 degrees Fahrenheit, whereas our water has a boiling point around 212. So the distance between our 173 and our 212 is our glide. We've actually been very successful at boiling off our ethanol out of our new mixture and leaving primarily water. You can see we got a few little bubbles of ethanol boiling off here, and we've lost a little bit due to just vapor, but I wanted to make sure that we were in atmospheric pressure during this whole experiment. And you can see we've actually got a pretty decent amount of our original ethanol in the container. So we're going to shut this down. It's been running for about a half of an hour or so. So we've been boiling out our ethanol along the way. Hopefully, that's exactly what it is. So we're going to shut it off. We're going to allow everything to cool down. And then we are going to see if we have water and ethanol, or tequila. All right, see you in a minute. All right, are we ready to see what we've got? Oh yeah, I am. So let's do a quick recap, right? So we have learned that glide is the distance between the points at which our chemicals boil or condense, right? It's that window in between their boiling points. And it creates a place that has two different points. It has the bottom, which we're going to call the bubble, and it creates the top that we're going to call the dew. So we know that in the middle, we can have a combination of chemicals that are, in a different state. So anything above the dew is going to be vapor. So that's what we use for calculating superheat. And then down at our bubble, we know that everything below that is liquid. And so we use that when we're calculating our subcooling. So I hope you see that we have two different boiling points. At atmospheric pressure, we had water that would boil at 212. We had our ethanol that would boil at around 173, which means we had like a 39-degree glide between those two. So the thing that we have to be concerned with is fractionation, because we do have that potential in certain scenarios in that glide window. Say we had a leak and we were leaking vapor out. If we were in the middle of that glide, we have the potential to leak one of our chemicals and not the other. Now, most of our manufacturers will tell us that even chemicals like 454B, which is going to be one of our new refrigerants in place of R410A on new equipment, it has a glide of a couple of degrees. And we're being told that it's not significant enough to need to replace all of the refrigerant unless it has been leaking for a very extended period of time. As you can see, even in this little experiment, it took a half an hour, 40 minutes just to be able to remove that small amount of ethanol. So we're not as concerned. We had between 0.2 of a degree and maybe 5 or 0.6 of a degree of a glide on R410A, because R410A had two different chemicals, R32 and R125. So we can see that in that glide, we have the potential for fractionation or fractionization, depending on how you hear it, and we can end up separating a chemical. So, are we ready to see? Did we actually separate our one chemical and not the other? Did we separate ethanol from water? Well, there's only one way to find out. We've had a little bit of time for it to cool down. Let's see if we have water or tequila. Definitely not water. So there you go. The fundamentals of glide, where we have a bubble point and a dew point, and we have a potential for fractionation or separation of our chemicals in between. So be aware that best practices would say if we have a leak in the vapor portion of our system and we're not 100% sure did we have fractionation, it's always best practices to replace refrigerant and add new. But our manufacturers are telling us that chemicals like R454B don't have a wide enough of a glide to contribute to excess fractionation. Some of our refrigerants out there, say like our 409, 407, 414, some of those had very wide glides, sometimes as much as 10 to 14 degrees. Those we definitely had a concern with. So going forward, we can see that we weren't very concerned about it with R410A, but we still inverted the jug to make sure that we got liquid refrigerant into our system. With R32, it is a single component refrigerant. Doesn't matter if the jug is vertical or if it is flipped upside down. Our R454B, since it is a blended refrigerant, it will have R32 and 1234YF. It really should be inverted, just like we did with the R410A can, so we make sure that we get liquid from the bottom of the tank and not potentially vapor that could be mixed, fractionation in the top. Thanks for joining us. All right, we have time for one additional lab experiment. You may not hear about this much in the HVAC refrigeration training, but when we're talking about chemicals, there's another fun little attribute that I always like to discuss. It's called sublimation. So we've talked about going from a liquid to a vapor, but what happens if we go from a solid to a vapor? Can we actually do that? Can we skip the liquid phase? We actually can if it's a drastic enough occurrence in a short period of time. That's what we're actually doing when we're working with our dry ice mixed with water. So if we take a look at this dry ice in our solution of water with a little bit of coloring, we can see that we truly are going from a solid directly into a vapor. We're boiling off past the liquid phase. We're changing phases so fast, we do not stay in the liquid phase. Straight from solid to vapor. And it's those vapor gases that causes the fog that we see. That's little small particulates of moisture, of water that enters into the air. But it happens because we were boiling our solid. Kind of interesting, isn't it? So sublimation is the act of going directly from the state of solid to the state of vapor or gas. It's very intriguing to watch. All right, what do you all think? Yeah. Chemicals make a little bit more sense now, huh?
I hope so. That was a good video.
Yeah, that was a lot of fun, right? You know, it really comes down to we're all here to learn and enjoy learning and to make education fun. And the only way we can do that is to just approach it, positively and professionally and add a little bit of character in between, right?
And I think you accomplished that.
I hope so. I really do. And, let us know what you want to learn next about our industry. That's what we're here for. And yeah, we might be a little bit goofy, but we got a lot of experience behind our belt and we have a lot of the right connections in the industry to help clarify things and to remove some of the stigma that you might be encountering. So let us know in the chat. Throw us an email, cbeck@escogroup.org. I'll throw that in on the finished video too, in case anyone needs to grab it. I'll just put it down in the description. Oh yeah, by the way, I will be heading to Ann Arbor, Michigan to the ITP week for the United Association, and man, that's gonna be a lot of fun. So tomorrow I'll be heading there, and I'll be back next Wednesday, and I'll have a lot of footage. We'll do some roadshow, and we'll talk about things that are happening in the UA and just education in general, and preparing all of our new generations for the equipment and the refrigerants and the things that are happening around us. Seems like super fast pace some days.
Almost daily, right?
Yeah, it's all changing, and that's why we're here, to serve you. So, Jason, I appreciate you so much.
Thanks for coming on. Yeah.
All right. We'll see you all next week.
In there somewhere, yeah.
Hey, who's that? They got the tools. He's back there somewhere. I think he's playing in some coal. All right. Everybody have a good week. See you next week on Did You Know? The ESCO HVAC Show.
Bye, everyone.